بسم الله الرحمن الرحيم الرحمن علم القرآن خلق الإنسان علمه البيان.
अल्लाह ताला ने हमें बनाया और बोलना सिखाया और अक़ल दी, बहुत कीमती नेमतें हैं। उसी के ज़रिए से सारे काम बनते हैं। So today we have covered the p-value last time. Now I'm going to explain the meaning and significance of the p-value. This is something about which the literature has a huge amount of confusion. And there are questions which are asked which nobody has answered. So basically the intuitive idea which we discussed is that if you have a null hypothesis, and now again one thing that I should explain is that what I am explaining is the null hypothesis in this course is not the standard definition. When I say null hypothesis, what we mean by this is the null hypothesis is the match between our theoretical model, which is an ideal world model, and the reality. So this is not the same as the standard definition or understanding of the null hypothesis. So now, if you reject the null hypothesis, then it means there is no match, or the match is not good. So now why do you reject? Well, basically, if the null hypothesis predicts something will be true, and what you see is something which is extremely unlikely, if the null hypothesis is this is impossible and that thing happens, then you should reject the null hypothesis. So we don't go to impossibility. If we tried to do that, then we would never reject the null hypothesis. And in fact, this is not a good, as a practical matter, this doesn't work very well. It's just a practical thing that in practice you cannot afford to take action only when you are certain. All the time in life we have to make guesses and then we have to act upon them. If you say that I want to have 100% surety about something before I make a decision, you will never make any decision in your life. So at all the time we are acting according to guesses. So again here in statistics we have the same issue. So a good rule of thumb, practical, is that if something has low probability, you should reject. So it's very simple. The idea that, okay, we set a critical value p star. If the event which happens has low probability, less than p star, we reject. And if it has greater probability, we accept. This is actually what we do. Now, the only issue is, why form this rejection region? Why not just take the event which happened and look at its probability? This is the most usual confusion. That if something very unlikely has happened, then you should reject. That's what we are saying. But now I say that no, don't look at that probability of the outcome which occurred. Take all of the outcomes which have equal or less probability. That is your rejection region. Calculate the probability of that rejection region, and that is the p-value. And that is what you should use to assess. So this is a little bit of a problem. I mean, why not look at what happened instead of what might have happened? This is actually a standard critique, that you are making a decision on the basis of something which might have happened, which didn't actually happen. So this doesn't seem like it's logical. So our first goal in this lecture is to explain why. So what we are doing, what I am saying to you is that if the rejection region has probability less than 1%, then we should reject the null hypothesis of match between model and reality, usually. And now you can ask me, look, 10 heads come up and this has probability 1 in 1,000, which is much less than 1%. So why not reject? I mean, why do we need to go through these complicated calculations of the rejection region and the p-value. On the same principle that you are teaching me, you can reject immediately. So this doesn't seem... Okay, so this has to be explained. It's a very important thing and it's not well understood at all. So we consider two people. One person is a doubting Thomas. And he always is in doubt about the null hypothesis. So he plans to conduct a lot of tests. He's going to do the test for excessive heads. He's going to do the test for randomness. He's going to do the test for independence. Let's say he's going to do 3 tests. And there's the true believer. He already believes that the model is true. So he's just going to do just one test. He's going to say if there's too many heads, then he's going to reject. And if there's not, then he's going to say, that's enough. I don't need to do further testing. Actually, the thing is that when you're testing for match, there are so many dimensions. You can do so many tests. We will show some of those today. And you can devise them. I mean, it's not something that there is only one test. You can be creative and you can think and you can devise as many tests as you like. So ultimately, there is no guarantee about, there's no one unique test which will decide that this is a good match. There are any number of tests that can be devised. So now the question is, think of these two people, doubting Thomas and true believer. Who is more likely to reject the null hypothesis? Well, it's obvious that the one who does more tests is more likely to reject. Now, suppose that, and we're thinking again, sequence of 20 flips of a coin is. See, this is very important. When you're talking in abstract, I'm describing an abstract principle, but in order to understand it, you have to reduce it. You have to translate it into the concrete. Human mind can only deal with concrete things. So if you look at the concrete, then you can understand, and then you can lift that understanding up to the higher level. This is the most important principle about trying to understand abstraction. It's because people don't understand this that mathematics is difficult, that you have to think simultaneously on 2 levels, on the particular concrete and specific level, and at the same time on the general abstract and metaphysical level. So now what we are saying is that let's look at a particular case. We have 20 coins are being flipped, and doubting Thomas is planning to conduct 3 tests on this, and true believer is planning to conduct only 1 test. So now suppose that doubting Thomas gets a lucky sample, one which is very nice and he fulfills all the model assumptions. So he is going to accept. He's going to run all the tests and all the tests pass. So he says okay. And at the same time, a true believer can get an unlucky draw. He gets by chance he gets 19 heads. It's unlikely, but it can happen. So then he will reject. So the fact is that doubting Thomas has a higher probability of rejection and true believer has a lower probability of rejection. But if you look at the outcome, the reverse happens. So it's not the particular outcome that we should evaluate. It's the general picture. So the p-value doesn't evaluate what is happening, it evaluates the plan. What do you plan to do? So it's your intention actually. How much testing are you planning to do? What testing is going to reduce to, what is the size of your rejection region? Now maybe you haven't even thought about, this is one of the objections. Suppose you don't think about it. Well, then we don't know what the p-value is. The p-value is telling us about what are your chances of rejecting the null. It's a pre-experimental measure. It is not a post-experimental measure. And the right thing to do, in some contexts, the right thing is post-experimental, some contexts, the right thing is pre-experimental. So there is this general argument that this general argument comes from this positivist philosophy, that you should only look at what happened, and you should never take into consideration what might have happened. This is ridiculous, but it is widely believed. So this argument is made that the p-value is a ridiculous concept because it depends on what you might have done. And people say that, look, suppose that this person rejects and here is this sample And he says that, oh, I was planning to do this, but actually his plan would have changed. Then his p-value would change. But they think that this is ridiculous, that because your action should depend on what you saw, not on what might have happened. And if what might have happened changes, then your action changes. So this is an argument that is made, but it is a wrong argument. Basically, it is correct that when you your rejection, the evaluation of the p-value depends on what you plan to do. Your plan to do is only known to you. So it is a psychological and subjective thing. And this is again against their philosophy of science, that you should not take into account psychological and subjective things. You should only look at the concrete. But just is not correct. All right. Now the second thing is that why not look at the outcome probability instead of the... so if we have an outcome which is very unlikely, then why not reject this? This is according with the same principle that we are teaching, that if the hypothesis says that something is very unlikely and that thing happens, then you should reject the null. Well, you see, again, you can understand this by looking at a concrete example. Suppose I take X as binomial with n trials and 50% success. So suppose n is 10,000, very large. So then we have 10,000 outcomes possible. Now you can calculate using the binom dist probability. What is the probability of each outcome? So now it turns out that for every outcome, the probability is less than 0.008. And actually, as the n goes to infinity, all probabilities go to 0. So every single outcome is very unlikely. This is very simple. Suppose you have 1,000,000 outcomes and all of them are equally likely, then every single outcome has probability 1 in 1,000,000. So all of them are very unlikely, but one of them will happen. So to say that something very unlikely happened and look at just that event doesn't make sense, because you have to look at everything together. So this is what happens, that so if we apply the principle that you are going to reject for less than 1%, then you will reject for all outcomes. And again, this explains why you have to reject. You have to check everything. Yani, that's why the rejection region must include not just the particular outcome, but all outcomes which are similar to that. Otherwise, you get the wrong answer. You will not get the so the p-value is a pre-experimental measure. If somebody is using a bad strategy but he wins by luck, this is a pre-experimentally bad thing, but post-experimentally it is good because he won. And conversely, if somebody is playing a very good strategy but the chance event happens that he loses, then pre-experimentally he is good and post-experimentally he is bad. Now the thing is that we want to evaluate the strategy, not the outcome, because this is this is what we should do. So that's what the p-value is doing. P-value is evaluating your strategy for the test. It's not evaluating what happens to you on that particular trial. What happens may be good or it may be bad. Your probability of success, your probability of getting to a good decision is high when you make a good plan. But you may make you may be unlucky, and with a good plan you may end up with a bad outcome, and with a bad plan you may end up with a good outcome. So that's not relevant. Alright, so that's the general philosophy of the p-value. Now we come back to a very important concept, which is that the space of outcomes is divided into two parts. One part, we still have this p star. This p star is the critical value. It's just that the p star is not the p-value. P-value is made by taking all outcomes with a probability less than p star and aggregating them. So we still have very simple structure of testing. We have a critical value p star. All outcomes which have probability bigger than p star are called the central values. They are the high probability values. All outcomes which have probability less than or equal to p star are called the unusual values. these are the probabilities we will reject for. So basically the space of outcomes is divided into two parts. One part is called the acceptance region. These are all the high probability values. And then the other part is called the rejection region, and these are all the low probability values. There's just one dividing line, and the only thing is that we adjust this p star according to what p-value we consider reasonable. And that's a subjective decision, as we have discussed last lecture, that it shifts from small doubt to more doubt to extreme doubt to almost rejection. So as we shift the p star, the p-value changes, and it changes from small conflict to more conflict to major conflict to massive conflict. So basically the general principle is that we should choose p star so that the rejection region has low probability, and 5% is the smallest probability at which we should think about rejecting, and it can be much lower also, we will see. So 1% or even lower than that is sometimes needed. Now, what happens very often is that we are not carrying out one test, we are carrying out multiple tests. And that's what we are going to show in this lecture. So the rejection region, so we have multiple tests, they have all their different statistics are used. So x1 is your first statistic, and it has its own rejection region, and x2 is another statistic, and it has its own rejection region. Again, you see, this is abstract, so I'm going to make it concrete very soon. Basically, we think of situation where I'm trying to match a binomial model to a long time series, and I want to ensure that the probabilities are not fluctuating. So I break up the time series into small parts, and then I check each part separately. So on the first part is the probability p, on the second part is it still p. See, I can do an overall test, which is what we did last time, but the overall test doesn't guarantee that the probability doesn't fluctuate in the middle. So if I have probability 1/2 for the whole sample, it may be that on the first half it was 75%, and on the second half it was 25%, and when I look at the whole sample it seems like it's 50%, but it's not actually true. So it's useful to do this breakup. So now I have, suppose we are going to look at annual data, and suppose I test each month separately. So I have 12 different tests for assessing the stability of the p-value. So now actually the rejection region is no longer 1, because I have to consider all of them, because I'm going to reject whenever one of those tests fails. So I can say that my rejection region, probability x1 falls in its rejection region, then I will reject regardless of what's happening in the others. Or if x2 rejects, so that's the region. And suppose that these are independent, every month is separate from the other. Then how to calculate this probability? This is very important to get the probability of the region. Now the thing is that it's difficult to calculate this probability, but there's a little trick which is used to make it easy, and that is to, instead of thinking about the rejection, think about the acceptance. So when you think about the acceptance, then you say all of the variables have to lie inside their acceptance region if we are going to accept. If any one of them falls outside, then we are going to reject. So then the event becomes probability x1 is in acceptance region, x2 is in its acceptance region, and so on. And these all events have to happen simultaneously. So this is an AND, this is an intersection. Now the intersection of the events, for that we have a simple rule for independent events, and the probability of an intersection is the product of the probabilities. So unlike that union is not easy. The intersection of events is easy. So we just multiply the 12 probabilities. Now for each one, the p value is the probability of rejection. So 1 minus p is the probability of acceptance. And so this will be just 1 minus p raised to the nth power. That's the probability of acceptance. And so if I take 1 minus this, I will get the p value for the overall tests. So this is the way to calculate for independent tests. When the tests are not independent, we will also consider that situation. That will be in the next lecture. That's more difficult.
So जो आपने breaks की जो बात की,
Hmm.
तो we will follow some particular test or do it intuitively.
क्या मतलब?
जो annual series की आपने बात की कि इसमें हम
अभी मैं करने वाला हूँ. I'm going to take a specific series and show you what to do. Okay, this is a graph of something. So I like to do things with explicit real world data. So I'm taking the data for okay, so I hope that here is it. This is the exchange rate. This is between Chinese yuan and US dollar. It is daily exchange rate from 2011 to just February of 2016. So it was 6.5795 on February 22nd, 2011, and 6.5741 yuans to $1. That means that the yuans appreciated, right? They became more expensive. Okay. So now, let's see, what did I do in this graph? I think I have it somewhere. I think I just plotted the this is just the exchange rate plotted directly. No. No, not yet. Okay, I think I need to open up the chapter right up. Okay, yeah. So this is the graph of the exchange rate directly for just 4 months, for the last 4 months. This is not the whole data set. So there's a lot of fluctuations. It goes up and down. Now, the thing is that the question, is this a random process? This is a wrong question. The question that we need to ask is, can we apply a random model which will have properties similar to what we are seeing? So basically, is there a match between a random model and this? Now, this immediately makes clear that, there are many different types of models we can make. So we can match, so this is a choice. Again, modeling is a choice. So when you think that the randomness is in the real world, then you have to find where the randomness is. But there is no randomness there. So when you realize that we are creating a model, then you have a lot of flexibility. You can think about what kind of aspects of this model, what aspects of this physical process could be well matched by a random model. So it's your choice how you choose to model, and I'm going to show you some choices. There are several different types of models that could be made. It is a creative act. Okay, so what I did was one simple way, because we are doing with binomials, that okay, so what I did was that we record a success if the yuan rate goes up, which means that the yuan actually depreciated because the number of yuans goes up. So I record a +1, and if it doesn't, I record 0. So now I have a binomial process. Success if the dollar appreciates, and failure if it doesn't. The doesn't case includes two cases where the rate remains the same and the rate goes down. It's not symmetric, but okay. So here is the graph of that process. So it goes up and down pretty erratically. So there is some hope that this will be a well matched to a binomial random model. Now, in this data set, there were 80 days. This is in the lecture notes. I did a different thing in the slides. Okay, so there were 80 days. This was the last 3 months. November, December, and January. January of this year and November, December. I looked at the last 3 months. There were 80 observations because there are weekends and holidays. There is no data for. So I divide, and so overall there was 37 successes. 37 in 37 days there was a depreciation, and in the remaining 43 days there was a failure. That is, the yuan rate either stayed the same or went down. So one thing is that one hypothesis that we could apply to this is that is it 50% the rate? Because some people think that, and there is some evidence that you should not be able to predict what's going to happen tomorrow. If you can predict that yuan is going to go up, then you can make a huge amount of money because there is a lot of people normally believe, this is called the efficient markets hypothesis. Eugene Fama is famous for this. So this says that nobody can make a profit, which means that it should be random. So it should be 50%. So now you just look at this. Is it 50%? Well, it should be 40-40, 37-43. You don't need to carry a statistical test. You can say that this is close enough. It will not reject the null hypothesis. So 50% is the hypothesis that the rate is 50%. With 50% probability it goes up, 50% it goes down, is compatible with the data. You don't need to carry out. Now the other hypothesis we could take is that, okay, I don't know what the P is. So we estimate the P from the data. It will be 37 over 80, which is 46.25%. Now, is this compatible with the data? Well, as we have said, this is the unknown P case. In the unknown P case, there's no point in testing for match because we already fixed the match. So there's no possibility that there will be excess heads or excess tails. So how do we test for a match? Well, one way, as I said, there's going to be many tests, and we're going to show many of these tests later on in this lecture. But one simple one is to divide the data into half and see if the probability remains the same on both of those halves. So when we do that, in the first 40 periods there were 16 successes, and in the second 40 you have 19. And together these sum to 37, of course. So the success proportion is 40% in the first half and 47.5% in the second half. So the deviation from 46.25% is fairly small, and we expect that there will be no rejection. You can, and for students, you should go through the exercise of actually calculating the p-value to be sure that you know how to do this. All right, now what we can do is we can subdivide this further into 4 parts of 20 periods, and When you do that, you find 7 out of 20, 9 out of 20, 11 out of 20, and 10 out of 20. All of these are very close to 47% probability, so again there is no reason to reject the null. One of the things is that when you subdivide, the power of the test goes down, because you see on a small, like for example, if you have 10 observations, then only 0, 1, and 2, and 8, 9, and 10 reject at the 5% level. Now the thing is that when you're subdividing, so there's only a very few observations which will reject, but it's even worse than that, because of the same problem. Now if you're doing 12 tests, then you can't do 5%, because at 5%, if you do 12 tests, your overall probability will be close to 50%. 12 times 5 is 60%, but there's some overlap. So that's too much. I mean, what is the p-value? This is important to understand. P-value is a probability of a type 1 error. That is, the null hypothesis is true, but you will end up rejecting. The null hypothesis is true. There is a good match, because the p-values are calculated under the assumption that the null hypotheses are true. So if it's 50%, that means the null hypothesis is true half the time, and half the time you will be rejecting it. That's very bad. You should keep that probability of type 1 error low. So it turns out that you have to reduce the p-value in each test in order to get an overall probability which is decent. So even if you keep it at 1%, your overall probability will be like 10%, which is too high. So you have to go about half of 1% for each test. But now if you make it half of 1%, then it's almost that there will be no rejection in any one of the regions, because the two extremes, 1 and 5, have probability 1 in 1,000. So you can reject at 1 in 10. But if you suppose you increase the number from 12 months to 24 months, then there will be no rejections in any sub-period. So the point that I'm trying to make is that as you subdivide, so the power of the test is the ability of the test to reject. So as you keep subdividing, you're testing more and more things, but the probability of your test picking up something becomes smaller. So this is a standard problem. If you do more tests, you can catch more things, but the chance of your catching any one thing is smaller. So if you sharply focus on one thing, then you can pick up one problem very accurately, but then you miss a lot of other things. So you can't have both. If you try to spread out, then the power of each test becomes weaker. But so let's see. Now I'll go back to the spreadsheet. Alright, so what we did here was to create this sort of binomial variables. This is something that I wanted to show. Yeah. कहाँ पे अच्छा है सही Okay, so Basically, this is a if statement. Yes, now Excel has a very nice new statement, but this is actually only available, it's just has become available only very recently, a few days ago, I think. Which basically makes something which was very awkward to do before, multiple comparisons. Anyway, I'm not going to go explaining that one, the Excel. Probably it won't be available to you right now. But what we do is we look at the compare B15 to B14. This is our B15. This is the yuan rate in current period, and this is the one in the previous period. So if it goes down, we record a -1. If it remains the same, we record a 0. And if it is going up, then we record a +1. So there are three outcomes here. And so you see it's -1 here because 5720 went down from 5741. And then it's +1 here because 5749 goes up from 5720. And then a -1 is here because it went down. So that's the record of -1s and +1s, and this is for the whole period. So what I have done here is I have calculated there are 1218 periods. Each period is a day, but some days are skipped in the middle. So now the total of -1s was 575. I counted that by using this COUNTIF function, in which you put in a whole array, which was C14 to C1232, and then I set, is this equal to -1? So it says there are 575 cases like that, and then this one is it equal to 0? So there are 91 cases where there was no change, and then there's 552 cases where the rate went up. So then I split it into two halves. The first half was 303. That's 608 periods in the first half, and 38 zeros and 267 ones. And in the second half, it is 271 -1s, 53 zeros, and 285. So we have 47.2% is the overall percentage of -1s, 7.5% is the percentage overall of zeros, and 45.3% is the overall percentage of +1s. So overall, we see that the hypothesis of efficient markets is supported here, in the sense that, you see, this is something that should surprise us, that there is something very interesting, that we are making a prediction about the real world on the basis of theory, and now we are seeing that there is a very good match between the theory and reality. Why? So there must be something about this theory which is true, otherwise we wouldn't expect a match. If I make some random theory about how Chinese, for example, I could, and if you look at the graph, it's going down for some period and then it's going up for some period. So I could say, okay, there's a period when China's economy was weak and the yuan was going down, and then there's a period where China's economy became strong and the rate went up. So this is a hypothesis that you could easily make, and you could tell a story, but the story doesn't match what the data is telling us, because the data is saying that the probability of increase and decrease was equal, and it was the same in both the halves of the data. So the idea that there was a general downdrift in one period, see, if you believe this story that there is a general downdrift, then you will say that, okay, then I can go and gamble on this market and I can make money. But this suggests that you should not, at least up to this extent, that from day to day the fluctuations are random. Now on the part 1 of the data, which is the 608 points, it's 49.8%, which is slightly higher than the overall, 6.3% and 43.9%. These are the in the part 1 of the data, the first half, 600, and these are the same probabilities on the second half. Again, from the looks of it, it doesn't seem that we can reject the null hypothesis. Now, what we would start by doing in this data for a real data analysis is that we'll say that, okay, it's not going to be 50% and 50% because we have 3 events. There's equality also. So what's the probability there's of no fluctuation, no change? So our best guess on the basis of these 1220 points is that it's 7.5%. So the probability that there is no change is 7.5%. And is this remain the same over the 2 halves? Well, 6.3 and 8.7. So let's check that. This is the first check. So I look at 38. That is the number of zeros in the first half, and I say let's look at 38, and the 609 is the total number of trials in the first half, and 0.075 is the hypothesized probability, 7.5%, and then I look at the cumulative probability, and then I double it to get the other side of the p-value. I mean, there's less than 38, and then there's bigger than the opposite side of that. So that comes out to 26%, which is a very high p-value. So means that if I was to reject for this, then I would be rejecting the null hypothesis 25% of the time when it is true, which is too high. So I don't want to reject the null. The same thing I apply for the 53. This time 53 is on the opposite side, it's excess. So I look at 1 minus binom dist 53 because I want to calculate the probability in the upper tail, 53 and above. So 53, 609, 0.075 and true. That and then I double that to get the probability on the other side. So the p-value is 23%. Again, that's very high. We cannot reject the null. And then this is the p-value for the 303, which is the first half of minus ones. So this is 271. Yeah. So I look at the 271 and I match it to the 609 is the n, and now the overall probability p I calculate as 46.75% because 7.5 is taken by the equality. The remaining part should be divided equally between pluses and minuses according to the efficient market hypothesis. So that's basically, we have 7.5, half of that is 3.25. That should be subtracted from 50%, and when you subtract 3.25% from 50%, you get 46.75. So I check for whether the probability is 46.25% in the first half, and I get a p-value of 28%, so it's strongly compatible. And similarly, all the other 4 numbers have very high p-values. So there is no evidence that there is any mismatch between the null hypothesis and the data on this ground. So this is the data that I was just discussing, and this also shows you the binomial statements which are used to calculate the p-values, and basically what we get is that there is a test for equality is good. We have no problems. Now, just to continue the same kind of logic and argument, what I did was to subdivide into months exactly, but I didn't actually do months. I did let's do 30 periods at a time. So the 30 periods can actually go over the month, and okay, let me show you that. So there are 1200 periods, and there are 40 periods of 30 days each. So I looked at, in each period, I looked at how many increases and how many decreases. So this is the graph. This graphs 30-day periods, all 40 of them, over the entire period, and you can see that it fluctuates. It goes up to about 70% and goes down to about 19%. So not much. For this particular, with this level of coarseness, 50% is fine, because the difference between 50 and 47% is not noticeable on a period of side 30. So the question. So I looked at all 40 periods, and the maximum deviation was there was 8. 8 was the number of gains and 22 losses, and the maximum was 20. So 20 gains and 10 losses. So these are the numbers. Neither 8 nor 20 is very different from 15. Actually, the p-value of 8 is slightly on the rejection region. I think the value is p-value is 2%. 20 is very close to 15. P-value is 10%, so there's no problem about that. But if you look at the 8, if you looked at it in isolation, then you would say, oh, this is unusual. 8 is quite far from 15. So this is another thing that is important to understand, that this is a very common and easy way to use statistics to deceive people. You see, I know that I have tested 40 different periods, but you don't know that. So if I say, here, have a look at this period. In this period, we have 8 declines and 22 going up. Is this compatible with the null hypothesis? Obviously not. It's only a 2% event. This means that the yuan rate was depreciating over this period steadily, and the efficient market hypothesis is wrong. It's just either a deception or a mistake. And similarly, you can construct arguments, because a lot of the part of, I did this. I was trying to show that you can create a very good consumption function and take the consumption of one country and match it to the GNP of another country. And so I tested all pairs of the WDI data has lots of GNP series and lots of consumption series, and I found that the Australian consumption is very well matched to the Chinese GNP. There's a very good fit, and so I can create a hypothesis which says that the consumption of Australia depends on the GNP of China, and my regression is very strong. I have a high R squared, and it's very stable and robust. You can do all sorts of tests on it, and it passes all the tests. So I can say, look, this is the theory, and this is my proof by data. Of course, I didn't tell you that I tested all of the 200 countries worth of data, and I found only this one strong example, and all the others were not so good. There were some good other cases, but this was the best. So if you don't know how I have selected the data, then the probability calculation that you do will be very different from the probability calculations that I did, and you can easily be deceived. That's what the p-value, the fact that the p-value is a plan, it's not a particular outcome. But if you look at the particular outcome, you may get different and misleading and deceptive results. So with the 2% p-value, if we would reject, but if we correct for the experiment, then you would look at 1 minus p to the 40, and with p equal 2%, this is 55%. So the chances of our finding a 2% rejection is more than half. So if I did this test correctly, with the null hypothesis being true, more than half of the time I would find one deviation of 2%. So there's no nothing surprising about that, nothing unusual about this. This is not an unusual value, it's a central value. Yeah, I have described the p-values. So basically, this is the individual p-value for 1 month. So 5, 6, 7, 8, 9, these are the numbers that are in the relevant range. Less than 5 is so small that you would reject without doing any calculations, and bigger than 9 is so large that you would accept without doing any calculation. This is also very important, that you should develop a sense. You don't need to consult tables. You should understand what hypothesis is compatible with what observation. So if you flip a coin 100 times, which is fair, 50 is the expected value, but between 40 to 60 is the normal range of variation. Less than 40 is, now you start to doubt, but you don't know this in advance. After you do the calculations, then you understand. But then you should absorb this into your intuition, that this is about how it works. All right, so now another test that I did is, okay, so one thing that is well known about these currency rates is that they're supposed to be volatility clusters. That means that in some periods there is a lot of fluctuation, in others things are stable. So also there is something which is called momentum, that if things are going in one direction, they keep going in that direction. So this is not correctly labeled. I think I'm testing here for not volatility cluster but momentum. So what I did was I said, okay, let's do the following. Let's look at a sequence of 4 ones, 4 minus ones. That is 4 declines in a row. Okay, so that's the volatility cluster. So this is the data. This is the first series, the -1 and 1, depending on whether it's going up or down. Now this is the second series. This is the function which, based on, it looks at are there 4 minus ones in the previous 4 periods. So in this period, is there a -1? Is there a -1? If all 4 of these are -1, then this comes into action. If they are not, then it marks it as a -1, means that it's out of the picture. Now if it is in action, then there are 2 things. Either the result is +1, or it is if it is -1, then I record a success, that okay, the momentum is there. That is, there were 4 -1s, and the 5th one is also a -1. So I record a +1 as a success trial, that okay, we have momentum. If there are 4 -1s and there is not a -1, it can be 0, it can be 1, then we don't have momentum. So I record a 0. If there are no 4 minus, then I say that this is not part of the game. So I record a 0. So there are these 3 outcomes here. So these -1 show that there is no game being played. There were no 4 -1s. Okay, here's my first +1. This is a momentum. I have 4 -1s in a row, and then it is followed by another -1. So I have momentum here. Now -1 means that this is not part of the game. Oh, here are 2 ones. This is momentum, and this is also momentum. I should have some zeros to show also. Because I counted them. Here are 2 more ones. So if there's only ones, then that shows a lot of momentum, and that proves that this hypothesis is true. That and also applies. That means that if you see a decline of appreciation of yuan for 4 days in a row, you should go and buy yuans because they are going to appreciate more. But actually, it's not like that. There are lots of zeros. Here's the first zero. No momentum here, and so on. Okay. Now I did a count of this. How many zeros and how many ones? And I think I have the record on my slide. So I found that there were 23 ones and 32 zeros. So first of all, what do you think? We'll reject the null hypothesis of 50% probability or not? It's 23 plus 32. This is the total number of cases. And in this case, we don't know how many cases there will come up. So we just add up these two. 55. So it's 55 cases. The expected number for exact equality would be 27 and a half. So 23 deviates from that by only 4 points, and basically 5 is 1 SD for 100. This is so. For a sample of size 55, the SD will be lower. Actually, some rules of thumb. Basically, when you double, the SD increases by square root of 2. It doesn't double, it multiplies by 1.4. So when we half the sample size, then the SD will go up by about this factor of 1.4. So it will be more than 5. So we are less than 1 SD away from the mean. So there is no chance of rejection. So it means that there is no momentum. So if you there's no momentum, it means that if you look at 4 different declines and then you decide to go in the market, you will lose, because the 4 declines don't give you any significant information. Now, I was doing a number of tests, as I said, and I did one which led to a very surprising result. This seems to reject the efficient market hypothesis. Just last night I was doing this. I said, okay, let's look at another possibility. We will say that the market is down if in the last 10 periods there are 8 or 9 or 10 minus 1s. These are the 3 values which are significant, remember? So that means that over the past 10 periods, 8 of the times the yuan appreciated, or 9 times it appreciated, or 10 times it appreciated. So this means that we have a significant evidence that in this period there is appreciation going on. So now what happens? So now I check again the same thing. Is it now in a down period, do we have minus 1 more or do we have less? So I found that in down markets, then the next period, after the 10, we look at the 11th one, and it is 32 minus 1s and only 2 1s. There are a total of 33 periods in which the last 10 periods have 8, 9 or 10, and in 34 of them, out of those 34, in 32 of them we have minus 1s recorded, and in 2 of them only plus 1. So this is a very strong departure from the 50-50 pattern. It means that if you test for a significant appreciation in the past 10 days, then you can bet on yuan appreciating on that with probability 32 over 34, which is very high. And similarly, I did the other hypothesis. Suppose the market is up, you have 8, 9 or 10 plus 1s. Then will it keep going up? So when the market is up, this means that the dollar is appreciating and the yuan is depreciating. So in that case, I found 24 plus ones in the 11th period and 5 minus ones. So again, this is strong, not as strong, but still strong and significant. So it seems that the trends exist. However, there is some problem with this result. The p-value here cannot be calculated directly for many reasons. That's because basically we have a lot of dependence. These are not independent events. It's very important. These are not independent events, so we can't, because you see, if you have 10 minus 1s, the 11th one, that's fine. But now, if you move to the next period, you automatically have a sequence of 10 minus 1s because there were 10 and you added 1. So now the next one is automatically in a down period. And this is not an independent. If we were looking at a separate set of 10 periods, then we could consider this as independent. But now it's the same 10 that we are taking into account again. So I don't know. So the independent formula for the p-value does not apply. So I can't just evaluate. I can calculate the p-value for any one of these events, but I cannot combine the p-values here. So the dependence is rather complex. You cannot actually calculate it very easily. And there is a technique which we use, and that technique is the simulation technique. And I will talk about that in the next lecture. So, how do you calculate p-value when you don't have independence? That's going to be the topic of the next lecture. In this lecture, I think we are going to conclude that. Is there any questions on anything we did? Oh yeah, I wanted to show the Excel a little bit, yes. Okay, so I wanted to show, I told you about the Excel calculations, but I wanted to show you how I did them. Okay, yeah, there are a few tricks that you should know. This is the same data. This is the original data set that we used, zeros and ones. Yeah, okay. Yeah, this is marking if B3 is greater than B2. So if we have an increase, it should be plus 1. And if we have a decrease, this should be plus 1. So this is the increases. And can you see this, or should I increase? Huh? This is increase, and this is decrease. All right, so now
डबल क्लिक कर दें
किसके ऊपर? अच्छा,
कस्टम उसमें डबल क्लिक करें.
okay, so where did I do that? Maybe not on the sheet. Ah yes, this is where I used a trick which is I wanted to show you. Yes, so this is how I divided the data into 30 non-overlapping periods. First of all, I copied the data and okay, those are just the dates, don't worry about them. We don't need to see them. So I copied the data over, and now I wanted to calculate yeah, right, okay. So this is these are the numbers which are -1. This is going down, +1 is going up, and I think this is all. Yeah, this one is the simple situation of -1 means that there is a decline, and 1 means there is no decline. So zeros and ones have been aggregated. Then this number, which I copied from another sheet, is just counting the number of declines in the next 30 periods. This 19 is the number of declines in the next 30 periods, and so on. So these are overlapping periods. So I don't want overlapping periods because that creates complications in calculating the p-value. But now I want to pick out this number, and then the one after 30 periods, and then one after 30 periods, and 40 of them. So that will take a long time if I pick them out by hand. So I did this by, I create a row. This is row number 2. This is row number 32 that I want. Row number 62 that I want. These are so I just wrote down these, and that can be easily done. It goes up to, this is an Excel sequence, standard. Then what I did, that's the thing that is I wanted to show you. I said indirect quote A and E2. So now E2 is this 2. So this basically picks up the cell entry in A2, which is the day here. And that's 223. It reformats the date for some reason, I don't know. And then I do indirect B and E2. And so this is 67%. This is just D2 over 30. This is 20, which is the number of days, and I just divide by the denominator to get the percentage. So this picks that up. Now the next one is indirect A and E3. So now this is going to pick up A32. The entry in A32, which is what I want, the 30 periods later. So the overlap is gone now. And this picks up B, which is 53%. And you multiply by 30 to get 16. So if you want to look at the percentage, this is here, and this is the count. So again, this is indirect of A and E4. So this is A62, and this is B62. So basically now I have my table which I want of the 40 periods of 30-day changes, and then I look at all of the
यहाँ पे जो overlapping आ रही है 16
no overlapping.
जो fourth के बाद जो second 518 वाली है यहाँ पे 16 आ रहा है.
क्या मतलब?
ये 53% and same 16.
Oh, that's because in that period, in that 30 months there was 16 increases, and the next one there was also 16 increases. It's not overlapping. It's just that the probability of 16 is high. 15 is the most likely value at 50%, and 16 is very likely. So you can have it twice in a row. So then basically what I looked at was the maximum and the minimum to get. So this is the minimum was 8, and the maximum was 20. So there is not that much deviation away from 15. If one of these was 0 or one of these was 5, actually 5 would be quite strong deviation from 15, and even in 40 periods we would say that there is something wrong about the null hypothesis. This is the graph of the percentages, and this graph, you see, basically 50% is what we expect to see in every period, and so the fluctuations are away from 50%, but not very large. And basically our p-value says that the null hypothesis that the true probability is 50% in every period is matched by the data. The data fluctuations are due to randomness, and they are due to random deviations away from 50%. So this is one of the keys that runs through the whole course, and also is the central, that 50% is your true value. The observed value is something different, Now, is this difference significant or not? So if we see 60% as the observed value and 50% is the true value, should we reject the null hypothesis of fairness or should we not? Now, if your sample size is 100, then you will not reject 60%. It's close enough. It's 2 standard deviation. If the sample size is 1000, you will reject. 60% is too far away from 50% because in 1000 the fluctuations are not that large away from 50. This is the law of large numbers, that as you increase the sample size, your deviation of observed frequency from the true frequency is low. So these are the calculations that we want to make. Okay, these are the calculations that I used for the 4 periods, and also basically something like that. Here it is. This is the significant data calculation. So I look at if sum C4 to C13 is greater than 5.5. You see this in this one I have set it up as +1 for increases and -1 for decreases. So now if you have and I'm looking at 10 periods. So if there is exactly the same 5 + 1 and 5 - 1, it will be 0. So if there are 8 +1s and 2 -1s, you will have a 6. So that's where I want to pick it up. So 8 +1s and 2 -1 is greater than 5.5, and then 9 is also going to give us 8, which is greater, and 10 is going to give us. So 6, 8 and 10 these are the 3 values for which I consider that my previous period is a period of significant increase. And then if there is a significant increase, I just mark this. This is zeros for zero if there is no significant this is not an up period. So zeros are all showing up periods, and there are no up periods here. There are going to be only a very few. Was there a one in there? Yes. So this is one in which we have 2 -1s and 8 +1s in the previous 10 periods, right? So this was one, and now I look at the product of this C and this. So if this is also a +1, this will come out as a 1, and otherwise it will come out as a 0. So this one shows that okay, there is momentum. I mean, in a significantly strong period, I had with 8 successes, I also got a success in the 11th period. So this is a 1. So then I counted the number of 1s in this, which tells us the number of periods that we had of significant ups. Here is another one, and here's again a corresponding one. Here's another one and another one. So we are seeing what is a pattern, that if you have okay here no yes.
तो फिर तो जो कॉलम सी में जो +1 और -1 का जो सीक्वेंस है, ऑर्डर है, वो भी मैटर करेगा मोमेंटम के लिए?
नहीं, for you see, this is something I am up free to think about the possible patterns that might exist and to test for them. And this again makes the p-value concept a little bit fishy, because I'm going to do a lot of tests, and then once I do a test, then I think of something else. Then the plan is not known. If the plan is not known, then the p-value is not known. So this is why, and again, it's inevitable, because sometimes there are possibilities that you think of after you look at the data. So ultimately, it's always a guess. Okay, now we have a lot of ones here. There is a sequence of declines. These are all 10 days of decline, and then in 11 days of decline, then 12 days of decline, then 13 days of decline. But 13 doesn't matter. We're only testing the past 10. So all of these 5 cases of declines are followed by another decline. So we have 5 consecutive ones, and then there is 1 0. Here there is exception. We have 10 days of decline and then an increase. So, and this one again, this falls out of the pattern. You don't have significance, and then you don't have significance. Anyway, so okay. So that's how I did the calculations, and the calculations seem to show that there is a strong that the hypothesis that the market can be down or up, and this makes a difference, seems to be true. Exactly. All right. So that's all for today.